Galactic cannibalism, the quiet hunger of the Milky Way. When we close our eyes and imagine a galaxy, we often see a perfect spiral. A pale wheel of stars turning slowly in the dark. A symmetrical, peaceful, almost motionless. But no human being has ever traveled far enough to look back and see the Milky Way from the outside. Every portrait of our galaxy is a reconstruction. Astronomers build it from distances, motions, radio waves, clouds of gas, and the faint light of stars hidden behind dust. Piece by piece, they assemble a view of the enormous structure that surrounds us. And the picture they have found is not quite perfect. The Milky Way is a barred spiral galaxy, but its disk is slightly warped. Its stars rise and fall in subtle waves. Its outer regions are crossed by faint arcs and ribbons. Far beyond the bright spiral arms lies an immense halo filled with ancient stars, globular clusters, hot gas, and matter that gives no light at all. Our galaxy is beautiful, but it is not still. The calm appearance is an illusion created by distance and time. Galaxies change so slowly that a human lifetime cannot catch them in motion. Even 1,000 generations would see almost nothing. Yet over hundreds of millions of years, spiral arms shift, stellar orbits bend, satellite galaxies lose their stars, and entire systems are quietly taken apart. The universe is not a museum. It is a place of continual assembly. For more than 13 billion years, the Milky Way has been growing. Some of that growth came from gas flowing into its halo. Some came from stars forming inside its disk. And some came from smaller galaxies that wandered too close and never escaped. Astronomers sometimes call this process galactic cannibalism. The name sounds sudden and brutal. The reality is slower. There is no bite, no single moment of impact, no sound traveling through the vacuum. A galactic meal may last for billions of years. But slow does not mean harmless. A smaller galaxy can lose its shape, its gas, its clusters, and eventually its independent existence. Its stars survive, but the galaxy they once belonged to disappears. It becomes memory. It becomes structure. It becomes part of something larger. And tonight, as the world around you grows quieter, we can follow that process through the long history of our own galactic home. We can watch one galaxy slowly become another. Gravity is often imagined as a pull between two objects. A falling stone, a planet circling a star, the moon lifting the oceans of Earth. But gravity across a galaxy is more complicated. A galaxy is not a solid object. It has no hard surface and no clear edge. Its stars become gradually fewer as one travels outward, fading into a halo that may extend hundreds of thousands of light years. When a small galaxy approaches the Milky Way, the side nearest to us feels a slightly stronger gravitational pull than the side farther away. This difference is called a tidal force. It is the same basic effect that raises the tides in Earth's oceans. But instead of moving water across a coastline, galactic tides rearrange stars across distances almost too large to imagine. At first, the change may be small. The approaching galaxy continues along its orbit. Its stars remain together. Its central regions still hold their familiar shape. But with every passage, the uneven pull grows more important. Some stars are drawn toward slightly smaller orbits. Others drift outward onto wider paths. The galaxy begins to stretch, not like a solid object breaking, but like a loose bundle slowly coming undone. Two long tails may appear. One reaches ahead of the galaxy along its orbit. The other trails behind. Over time, these tails lengthen into stellar streams, faint rivers of stars following the path of a parent galaxy or star cluster that may already be almost gone. Some streams stretch for tens of thousands of light years. The largest wind around much of the Milky Way, crossing enormous regions of the galactic halo. They are not bright ribbons that the human eye could easily see. Their stars are scattered too thinly. Astronomers find them by noticing that certain stars share the same motion, the same age, or a similar chemical history. A stream may be almost invisible in an ordinary photograph, yet become clear when its stars are plotted by velocity and distance. It is a strange kind of archaeology. On Earth, archaeologists read broken pottery, buried foundations, and marks in ancient stone. Galactic archaeologists read motion. Every star carries a record of where it has traveled. Its speed and direction reveal the orbit it follows. The elements in its atmosphere offer clues about the cloud from which it formed. Iron, a magnesium, a calcium, a oxygen. Different galaxies enrich their gas at different rates. Their stars can therefore carry slightly different chemical patterns, like accents retained from a distant homeland. No single star tells the whole story, but millions of stars measured together begin to reveal ancient events. A cluster moving against the general flow. A group following unusually stretched orbits. A chemical signature repeated across the sky. The galaxy remembers, even after the original structure has disappeared. There is another reason the process unfolds so differently from an earthly collision. Galaxies are mostly empty space. The stars inside them may look crowded when we see their combined light, but typical stars are separated by several light years. Compared with those distances, each star is almost unimaginably small. When two galaxies pass through one another, direct collisions between their stars are therefore extremely rare. One stellar population may flow through another, like two clouds of fireflies crossing in the night. Most individual solar systems would not experience a star rushing close enough to tear away their planets. From the surface of a distant world, there might be no sudden flash and no obvious moment when one galaxy entered another. Yet its home star could slowly be carried onto a new galactic orbit. The night sky would change over immense spans of time. New stars might appear in unfamiliar regions. Old constellations would stretch and dissolve. The bright band of the parent galaxy might become broader, twisted, or crossed by another river of light. The stars pass one another. The galaxies do not. Their gravitational fields overlap. Their gas clouds interact. Dust and plasma can be compressed, heated, or swept away. In some mergers, this compression produces intense bursts of star formation. Gas may also fall toward a galaxy's central black hole, awakening activity that had remained dormant. So galactic cannibalism contains a quiet contradiction. For a single star, very little may happen nearby. For the galaxy itself, almost everything changes. As a smaller galaxy moves through the Milky Way's halo, it also creates a wake. Not a wake in water, but a subtle gravitational disturbance in the surrounding stars and dark matter. This wake pulls backward on the moving galaxy. Very gradually, the smaller system loses orbital energy. Its path shrinks. It circles closer to the center, where the tides become stronger and each passage removes more material. Astronomers call this dynamical friction. The name sounds ordinary, but there is no physical surface rubbing against another. It is gravity acting through countless distant encounters. The process can continue for billions of years. Orbit after orbit, passage after passage. The smaller galaxy grows lighter as its stars are stripped away. Its dark matter halo is usually removed first, because it extends far beyond the more tightly bound central stars. Later, the visible body begins to unravel. Eventually, only a dense remnant may remain. Then even that may disappear. But disappearance does not mean annihilation. The stars continue. They spread through the halo. Some join the thick disk. Some remain in streams for billions of years before gradually mixing with the larger population. A swallowed galaxy is not erased. It is translated into another form. To find one of the most important chapters in the history of the Milky Way, we must travel back roughly 10 billion years. Earth did not yet exist. The sun had not formed. The Milky Way was younger, more turbulent, and less massive than it is today. Its disk was still developing. Its halo was still gathering the remains of earlier systems. Into this growing galaxy came a substantial companion. Today it is usually called Gaia Enceladus or Gaia Sausage Enceladus. The second name comes from the elongated shape made by its stars when their velocities are plotted on a graph. It is not an elegant name, perhaps, but astronomy often gives poetic objects very practical labels. The exact mass and structure of Gaia Enceladus remain subjects of study. It was far smaller than the present Milky Way, but large enough to transform it. The encounter was not a single collision. The two galaxies passed through and around one another repeatedly. Gaia Enceladus lost energy, sank deeper, and was steadily torn apart. Its stars were thrown onto long, highly stretched orbits. Many now travel inward toward the central regions of the Milky Way, and then far outward again, like slow pendulums swinging through the galactic halo. The merger contributed a large fraction of the ancient stars in the inner halo. It also disturbed the early disk of the Milky Way. Stars that may once have traveled in a thinner, flatter layer were scattered onto higher and more energetic orbits. This heating probably helped create part of the thick disk that surrounds the thinner disk we inhabit today. The event did not simply add new material. It rearranged what was already here. This is one of the deeper consequences of galactic cannibalism. The larger galaxy is not an unchanged container receiving smaller objects. It is shaken, heated, warped, and redirected by every substantial encounter. The eater carries scars from the meal. For many years, these ancient events remained hidden. Then astronomers began measuring the Milky Way star by star. For more than a decade, the Gaia spacecraft repeatedly scanned the sky, recording positions, distances, brightness, colors, and motions. Its observing phase has now ended, but the archive it created continues to speak. Inside the movements of nearly 2 billion measured objects, astronomers can search for groups that do not follow the general rotation of the galactic disk. Some stars move on nearly circular paths around the center. Others rise far above and below the disk. Some follow stretched, radial orbits, plunging inward and then returning to the halo. When these motions are compared with the stars, ages, and chemical compositions, ancient populations begin to separate from one another. The remnants of Gaia Enceladus are not gathered in one visible cloud. They are spread widely across the sky. Some may pass through the region near the sunday. They look like ordinary points of light, indistinguishable to the unaided eye from stars born inside the Milky Way. Yet their paths are different. Their chemistry is different. They are citizens of the Milky Way now, but they were not born here. In this sense, the night sky contains migrations older than Earth. Every ancient star is traveling with a history. Gaia Enceladus belongs to the distant past. But galactic cannibalism has not ended. It is happening now. Toward the constellation Sagittarius lies the remnant of a dwarf galaxy that is currently being dismantled by the Milky Way. From Earth, the Sagittarius dwarf galaxy appears in a crowded direction near the galactic center. Dust and foreground stars make it difficult to see as a distinct object. Its stream, however, reaches far beyond it. Stars removed during earlier passages form vast arcs that wrap around the Milky Way in more than one loop. The stream is a record of repeated encounters written across the halo. Sagittarius does not simply circle at a safe distance. Its orbit carries it through regions where the Milky Way's gravitational field pulls strongly upon it. With each passage, more stars escape. Its surviving core grows smaller. Globular clusters that may once have belonged to Sagittarius are being inherited by the Milky Way as well. They may remain long after the dwarf galaxy itself has lost its final recognizable shape. But once again, the influence moves in both directions. The passages of Sagittarius appear to have disturbed the Milky Way's disk. They may have helped create waves, ripples, and vertical motions that astronomers now observe in nearby stars. Some studies suggest that its repeated encounters may even have influenced episodes of star formation. A dwarf galaxy can therefore be destroyed by the Milky Way while simultaneously reshaping it. The victim becomes an architect. The meal changes the one that consumes it. Farther across the sky are two companions visible without a telescope from much of the southern hemisphere. The large and small Magellanic Clouds. They appear as pale patches detached from the Milky Way, almost like pieces of the night sky that have not fully dissolved into darkness. For centuries, travelers used them as familiar markers in the southern heavens. Today we know that they are irregular dwarf galaxies, each containing its own stars, gas clouds, clusters, and complex history. Their relationship with the Milky Way is still being reconstructed. They may not be ancient, settled satellites that have completed many quiet orbits. They could be relatively recent arrivals to the inner regions of our galactic halo. They are also interacting strongly with each other. Between and behind them stretches an enormous system of gas known as the Magellanic Stream. Much of this material appears to have been removed from the small Magellanic Cloud, while part came from the large Magellanic Cloud. Their mutual gravitational encounters pulled gas outward, and their motion through the Milky Way's hot outer atmosphere helped strip and shape it. The stream contains a great deal of hydrogen, but much of it is ionized and invisible to ordinary eyes. Seen with radio telescopes and ultraviolet measurements, it reaches across a vast portion of the sky. It is sometimes described as fuel for future stars. That may be true. If enough of the gas survives its journey through the hot galactic halo, some could eventually reach the disk cool and become part of new molecular clouds. Within those clouds, gravity might gather the gas into another generation of stars. But the journey is uncertain. Some of the stream may evaporate. Some may fragment. Some may mix into the Milky Way's hot corona, instead of reaching the bright disk. Even then, the material is not lost. It becomes part of the larger circulation of gas surrounding the galaxy, perhaps cooling the halo or joining the disk much later by a less direct route. A galaxy does not merely eat stars. It also exchanges gas. It strips, heats, recycles, and transforms. The same atoms may pass through many forms: a dwarf galaxy's cloud, an ionized stream, the hot halo of the Milky Way, a future stellar nursery, and perhaps one day a planet. Cosmic cannibalism is also cosmic recycling. Beyond the stars and gas lies something more difficult to picture: the dark matter halo. Dark matter does not shine. It does not produce a visible shadow, and it has not yet been captured as a particle in a laboratory. Astronomers infer its presence from gravity. The stars and galaxies move too quickly to be held by the visible material alone. Satellite galaxies follow paths shaped by an unseen mass. Light from distant objects bends around galaxy clusters more strongly than luminous matter can explain. Around the Milky Way, dark matter appears to form an enormous halo, extending far beyond the bright disk. It is not a solid shell. It is an invisible distribution of mass, perhaps containing many smaller concentrations known as subhalos. Stellar streams travel through this unseen landscape. Because streams can be long, narrow, and dynamically delicate, even a passing object may leave a trace in them. A dark subhalo moving near a stream could alter the orbits of some stars. Over time, a gap might open. A section could bend or become denser than the regions around it. The stream acts like a slowly moving detector, or perhaps like the surface of a calm lake. The wind itself is invisible, but its passage can be inferred from ripples. The comparison is useful, although reality is more complicated. Not every gap must come from dark matter. Giant molecular clouds, globular clusters, the Milky Way central bar, and other visible structures can also disturb stellar streams. Astronomers must compare many possibilities. They study the stream's age, width, orbit, and density. They model all the known objects that might have crossed it. Only then can they ask whether an unseen mass offers the best explanation. The result is not a simple photograph of dark matter. It is a gradual reconstruction, a map drawn from consequences rather than light. And the more streams astronomers discover, the more carefully they can test the invisible architecture of the galaxy. The halo of the Milky Way is therefore more than empty space around a bright spiral. It is an archive. Ancient stars preserve the chemistry of vanished galaxies. Stellar streams trace disrupted satellites and clusters. Ripples in the disk record gravitational encounters. Gas clouds reveal ongoing exchange. The motions of all these objects help outline the dark matter that cannot be seen directly. Even the shape of the galaxy is a record of what has happened to it. The Milky Way did not form once and then remain unchanged. It is still forming. Its identity is layered. Some of its stars were born in its original disk. Others arrived with Gaian Enceladus, Sagittarius, or systems whose names and structures may never be recovered. Still others may belong to mergers so old that their debris has completely mixed into the halo. There may be no perfect boundary between what formed here and what arrived later. After enough time, the distinction becomes difficult to make. This leads to a quiet question. When one galaxy absorbs another, at what moment does the smaller galaxy cease to exist? Is it when its dark matter halo is stripped away? When its gas is lost? When its stars no longer remain together? Or only when there is no longer any observer capable of recognizing their shared origin? Galaxies have no official borders. They do not announce their beginnings or endings. They fade into one another. Far beyond the Milky Way, about 2.5 million light-years away, lies the Andromeda Galaxy. It is visible to the unaided eye under a dark sky, a small, soft blur, carrying light that began its journey long before modern humans existed. Andromeda is moving toward us. For many years, the familiar prediction was simple. In roughly 4 or 5 billion years, Andromeda and the Milky Way would begin a great collision. After several close passages, they would merge into a larger, rounder galaxy, sometimes nicknamed Milkomeda. That future remains possible, but it is no longer the only future allowed by the measurements. The sideways motion of Andromeda is extremely difficult to determine. Small uncertainties become enormous when its orbit is projected billions of years forward. The Large Magellanic Cloud and the Triangulum Galaxy also influence the calculation. Their gravity can alter the paths of the two larger galaxies in different ways. Some current models still lead to a merger several billion years from now. Others allow the galaxies to pass at a greater distance and remain separate for at least 10 billion years. The answer is not yet settled, and that uncertainty is not a weakness. It is an honest picture of science at the edge of measurement. The universe has already chosen what will happen. We simply do not yet have enough information to read the decision. If Andromeda and the Milky Way eventually meet, the event would unfold over a span of time longer than the present age of many species. At first, Andromeda would grow larger in the sky. Its disk would become visible as a great band of light. Tidal forces would begin to stretch both galaxies. Their outer halos would overlap long before their bright disks made a close passage. Stars would mostly pass one another without direct collision. But their orbits would change. Some would be thrown farther into the combined halo. Some would move inward. Great tidal tails could extend into intergalactic space. Gas clouds would interact more directly. Regions of compressed gas might produce new stars. Other gas could be heated or expelled. The central black holes of the two galaxies might eventually sink toward the center of the remnant and much later merge. The final galaxy might become more rounded and less obviously spiral. But even then, nothing would truly be final. It would continue to orbit within the local group. It would still possess satellite galaxies. Gas would still move through its halo. Stars would still form and die. Smaller systems could still approach and be absorbed. There is no last meal. No permanent resting shape. A galaxy is a process, not a finished object. Perhaps this is the most important idea hidden inside the dramatic phrase galactic cannibalism. A galaxy is not one simple thing devouring another. It is a meeting of histories. The smaller system loses its name and its form, but its material remains. Its stars continue to shine. Its clusters continue to orbit. Its chemical elements enter new clouds and perhaps new worlds. The larger system survives, but it does not remain the same. Its disk thickens or ripples. Its halo grows. Its center may brighten. Its stars are carried onto new paths. Neither participant leaves the encounter unchanged. One identity disappears. Another becomes more complicated. And our own galaxy is filled with these complications. The Milky Way is not a single, untouched island. It is a gathering place. A layered structure made from ancient clouds, vanished dwarfs, scattered clusters, streams of gas dark matter, and generations of stars born from material that has traveled through the universe in many different forms. When you look into the night sky, you are not seeing a perfectly settled home. You are looking into an unfinished history. Some of the stars above may have formed inside galaxies that no longer exist. Some may have crossed the Milky Way disk many times, carrying the memory of an ancient collision in their motion. Some may eventually drift far from the region where we see them tonight. Nothing in the galaxy is truly standing still. But everything moves so slowly that, for this moment, the sky appears calm. The Sagittarius stream continues along its immense orbit. The Magellanic gas moves through the halo. The ancient stars of Gaia Enceladus travel on path established billions of years ago. Andromeda approaches, although its final destination remains uncertain. Gravity continues its work without hurry. There is no need for haste on the scale of galaxies. A single orbit may take hundreds of millions of years. A merger may unfold across billions. A stream may remain visible long after its parent has disappeared. And while all of this continues beyond the night, the Earth turns gently beneath the stars. The Milky Way stretches across the sky. Not perfect, not motionless, not alone. A galaxy made from other galaxies. A home built from travelers. A quiet river of ancient light, carrying countless histories through the dark. And for now, as those distant stars continue along their enormous paths, there is nothing more you need to follow. The galaxy will keep moving. Gravity will keep gathering. The streams will continue their slow journey. And the night can simply remain around you. Vast, unhurried, and deep.